Hello and good evening. My name is Jamal Sabadugo, and this is my CSTR design equation for my CBE final. So, first of all, we're given this question right here. Component A is fed into the inlet stream 1, and component B is fed into inlet stream 2. And the rate of reaction of species A equals CA 0.5, CB 1.5. KO in this case equals 0.31 liters per gram moles times seconds. The reason I have this written down is because in previous attempts, writing everything down took well over 10 minutes. Therefore, I will glance through the questions and glance through the graph, go into detail on why we're having these problems right here before solving them in 7 steps. So without further ado, let's get to it. The reactor has the following characteristics. The system is at constant density of 0.98 grams per centimeter cubed. The volumetric flow rate of steam 1 is 12 liters per second. The mass flow rate of outlet stream is 63.3 kilograms per second, which is important for the kilograms. Entering concentration of A equals 1.9 gram moles per liter. Entering concentration of B is 2.7 gram moles per liter. And the conversion of species A is 0.54 and of species B is 0.74. So given all this information we have over here, we're looking to solve the problem, which is what is the required volume in liters? And here's the equation given. A volume equals FAO XA over RA, and we'll look into what these all mean. FAO means the molar flow rate of A entering. XA is the conversion of A, which is 0.54. We could just substitute 0.54 here. At the end, we will. And RA would be the rate of consumption of A at the exit, and it's measured in gram moles per liters times seconds. Okay, so the little graph, the little image we have over here would be our CSTR reactor. So we're reminded of the values. We know there's going to be 2 inputs, and there'll be 1 output for the outlet stream. And we know that it will be at a constant density of 0.98 grams per centimeter cubed. For stream 1, we have 12 liters per second for the volumetric flow rate, as it is given here. For stream 2, we have 1.9 gram moles per liter for the concentration of A entering the system. The outlet stream of the mass flow rate is 63.3 kilograms per second, as we set up here. And what we're looking for is the volume of this CSTR reactor as a whole. XA is 0.54, XB is 0.74, as said above as well, for the conversion of species A and species B. Okay, so we will split this up into 7 steps. The first step would be to find FAO, which is the molar flow rate of A entering the CSTR. So it is as followed for FAO for the equation. FAO would equal CAO multiplied by Q1. So CAO in this case, we have it from what was given to us. CAO in this case would be 1.9 gram moles per liter, because it is literally just our inlet concentration of A. And Q1 would equal 12 liters per second. 12 liters per second and 1.9 gram moles per liter. And we multiply both these values to get 22.8 gram moles per second. CA for step 2 is to find the concentration of A at the outlet. So we're reminded that XA equals 0.54. And the equation for CA would be CaO 1 minus XA would give us our answer. So CaO, CaO, as we went over, is 1.9. And then we will input 1 minus XA, which is 0.54. In doing the math, we will come up with the answer of 0.847 gram moles per liter. And that would be what C of A equals for step 2. As for step 3, the volumetric flow rate, aka Q out, is what we're looking for. And the equation for that would be dot M over P. M in this case would be the outlet mass flow rate, so it would be the 63.3 kilograms per second. And P would be the density, which is 980 grams per liter. So we have an issue here because this is in kilograms, this one is in grams. So we either move this up to kilograms or move this down to grams. I would pick to move this to grams by multiplying it by 1,000. So let's just go ahead and do that. We'll do 63,300 grams per second over 980 grams per liter, which would give us the answer of 64.59 liters per second for our Q out value right there. Now we're gonna look at the molar flow rate of B entering, or FBO. We're first gonna find what Q2 is, which is the flow rate of stream 2. And Q2 is literally just Q out minus Q1. Q out is what we got here, which is 64.59 liters per second, minus Q1, which would be 12 liters per second, which would be 52.59 liters per second right there. Now, to find FBO, we would literally just multiply our value of 2.7, which reminded again would be 2.7 grams would be the entering concentration of B. So it'd be entering concentration of B multiplied by Q2, which is 52.59. And the answer would be 141.993 gram moles per second. Moving on to step 5, concentration of B at the exit would be the equation of CBO 1 minus XB. So CBO would be 2.7 again as concentration of B entering 2.7, and that would be 1 minus XB, which we know as 0.74. We can use our calculator and find the answer, which is 0.702 gram moles per liter. Step 6, we're gonna find RA. Now RA is a little bit heftier, but is literally just using the values we already have. So R is KO times CA 0.5 times CB 1.5. KO we know is 0.31. CA would be 0.874 given to us in the beginning, times 0.5. And CB would be 0.702 to the 1.5 exponent. Now this would be the exact same as saying 0.702 times the square root of 0.702 because of the 1.5 exponent here. And this number right here is the square root, would be 0.874 times 0.5 power, which is 0.9349. And this value right here would be 0.5884. All in all, we do 0.31 multiplied by 0.9349 multiplied by 0.5884 to get 0.1707 gram moles per liter times seconds. Okay, so now the final step is to plug in all these values that we have. So we know that volume equals FAO, which is 22.8, multiplied by 0.54, which is our constant XA over here, over RA, which we just got, which is 0.1707. So using our calculator and doing the math, we will end up hopefully with 72.1 liters. And this is our final answer right here. Thank you very much for listening. Bye.